Good morning. In this video we will see Azer Pro 3D Piping and Azer Pro Isometrics, the two modules for 3D model and isometric sketch generation. In the first part we will see in particular the integration between the Azer Pro 3D Piping module and the Azer Pro PNID module that we've already seen in the previous video. The Compare with PNID palette allows to compare the 3D module with what has been drawn inside the Azer Pro PNID module. By opening the drawing, all the objects in the PNID scheme are shown, and according to the color, we are able to recognize the objects that have not yet been inserted in the piping. They are the white objects. The green objects, however, are present in the piping and can be highlighted. The red objects are present, but they have been modified, misaligned objects. In this case, we see that the pump model in the process scheme has been modified. It's been changed from MC to MCX, as well as other data such as engine power. By clicking on Show PNID, you can also open a floating palette where the components are highlighted in the diagram. By clicking on Disable Colors, you can turn off the original colors, and at this point, according to the state of the component, we will see the modified objects painted in red, in grey for those not yet inserted, and green for those already present in the 3D model. In this case, we see that changes made in the PNID have no impact on the 3D model. Then we can simply resynchronize the data. We now create the vessel TKey001, which we have in the PNID, but not yet in the piping. Take a reference point, type an elevation, 800 millimeters, and launch the Vessels command. Inside this window, I have a set of parametric vessels that I can choose from, and for each of them I can specify the dimensions. 2,200 millimeters is the length and 1,400 millimeters is the distance between the saddles. Pick an insertion point and specify an orientation. Azer Pro 3D Piping asked me to assign a tag and characteristics to this tank. In this case, it's not necessary because I've already specified them in the PNID scheme, and with Associate Object, I can link the two objects. At this point, I have the same data in both environments, and if I check the diagram, I see that the vessel has become green. Once the tank is finished, we can now focus on the nozzles. Close the integration browser, and let's take a reference point from the tangent line of my vessel. I take the center point and type in a 400 millimeter offset that will be the starting point of my nozzle. I launch the nozzle command, and from the dialog I choose a class, a diameter, and the type of nozzle that can be flanged, threaded, physical or logical. Logical nozzles are attachment points of equipment imported as step files. Let's give a diameter to our nozzle and pick a starting point. We indicate the orientation, in this case we draw it upwards, and type in the length, 800 millimeters up and 400 millimeters to the left. Once the nozzle is drawn, we press Enter and select the equipment body. The nozzle has been modeled and we can give it a name. N1 in this case. Now let's draw an eccentric nozzle that we will name as N2. We pick a point on the axis and set the offset, in this case 200 millimeters. This will become the starting point for the new nozzle. We choose a diameter, 4 inches, first point, length, 1,000 millimeters. And at this point we select the vessel body. We gave a name to the second nozzle. Actually, the nozzles are separate objects, so you can move or delete them once you've finished creating your equipment. Let's see the Azer Pro 3D Piping commands for generating the steel structures. Let's make an example and go draw a frame. So let's draw a rectangle with AutoCAD. We explode the polyline and copy the lines to create the construction lines. Once the outline is done, we launch the commands to create the steel structures. In addition to the shape command, we have a set of commands that allow to solve the intersections with 45-degree cuts or shaping. Let's choose the HE shape. We select the beam alignment point, in this case it is the lower side, and pick a set of points. As an alternative, it's possible to invoke the same command, and selecting the line option, you can select AutoCAD lines and dress them with beams. Let's fix this junction with the fillet command. The fillet command cuts the edges at 45 degrees. In this case, we will use the increase-decrease length command to fix the intersection. This command, in fact, allows you to lengthen a shape, or as in this case, to shorten it. To resolve the intersection of the inner beam, we will use the subtract from shape command. With this command, it's possible to shape the beam by selecting the two beams that will be subtracted. Another very useful command for fixing the intersections is the trim extend shape command. This command allows you to select a face and the beam that you want to cut. Its behavior is similar to AutoCAD's cut and extend commands. In addition to individual beams, it's possible to create standard configurations. In this case, we're going to generate a pipe rack. The rack isn't actually a single object, but is made up of single beams, which can be copied, moved, or stretched when needed. We copy the horizontal beam, and with the trim extend command, let's stretch the vertical shape under the horizontal beam edge. We finish by copying the two reinforcements, and we have therefore created a customized rack. In addition to racks, there are other standard configurations such as range poles, squares, and columns. Let's create a configuration of 4x3 on which we're going to place a grating. We start by drawing a 2D contour that will serve as a guide for our grating. We draw a standard AutoCAD polyline and add a round boundary, a circle, which will be a hole inside our grating. Then we take a reference point at Z elevation and launch the circle command. Once the outline has been drawn, we launch the landing command, grating type. Select the outer contour and the inner hole. The grating is created automatically. We use the AutoCAD Move command to raise it to the proper elevation. Now we're ready to go draw the handrail. With the command railing, I can pick a set of points or select a polyline, as we did previously. In this case, I pick some points that define the boundary of my handrail. Let's go now to add a stair. The stair command gives me the possibility to size my staircase, specifying a height, a number of steps, and a tread width. In addition to this, I can also choose if I want a grating or railing or even a landing. I give a starting point, a direction, and my staircase is generated. Now let's move the staircase to match with our grating. The objects are AutoCAD solid, so we can use the usual commands, and then use OSnap to get the points. We match the edge of the stair to my beam and then go to move it. the steel structure is complete. As an alternative to the staircase, we could also have created a ladder. With the ladder command, we can add a ladder, which may also include a safety cage, or in the case of circular tanks, we can also generate spiral stairs. Also, in this case, we have the possibility to modify all the dimensional parameters. After this overview of steel structures, let's apply the commands to draw support for our piping. Here we have some lines that we use with the beam command to dress them with beams. Select the top of steel alignment and the line option. These beams will be the supports for our pipes. The beams we are creating can also be counted in the bill of materials. And most of all, they can be used as a base for the ESA Pro Supports module, where we can represent the constructive support in detail. We insert the beam and rotate it, and with the trim command, we will clean the intersections. Trim on a face. 1, 2, 3, and 4. We must also trim the lower side, so using the orbit command, we change the viewpoint and select the lower face as trim limit. These are AutoCAD solids, so you can also use the Boolean modeling operations. We're ready to create the piping, but before we start modeling the pipelines, let's take a look at ESA Pro's parametric catalogue. It's a large dimensional catalogue consisting of hundreds of thousands of parts. The parts are organized in parametric tables within a hierarchical structure with multiple levels. The first level is the category, the second one is the family, and the third is the typology. For each typology, we have different dimensional tables according to the various standards: American standards, ASME, or metric standards, ISO, DIN, EN, etc. In addition to the most common components, we also have special components, such as plastic components, or fittings for compressed air. It's therefore a catalogue that suits the different types of plant that users may need to design. Let's now take a look at how a typical dimensional table is organized. Let's take, for example, a table of flanged gate valves. In this case, ASME 150 pounds. These are the dimensional parameters used to create the object: H, V, L, and D. The blue columns are the mandatory ones, while the yellow ones are optional, and may also change according to the manufacturer. We've 5 description languages, and we can change them to suit our needs. As well as dimensions, we can enter the weight, part number, and other data. Tables provided by ESA Pro are just a base that can be reused through copy-paste. Beside the piping objects, the matching P&ID symbol is shown because the two environments are integrated. We now create a new piping class by selecting the components from the catalogue. Let's create an example class for water named W001. Only the objects we add to this class can be used to model our pipeline. So let's add the pipe, the elbows, butt welded and socket welded, equal T's, butt welded and socket welded, and half couplings to connect pipes with different diameters. Some flanges, welding neck in this case, with compatible gaskets and bolt set. Once we've added the components to the list, we choose which tables from the catalogue to use. We then select our pipes table, the range of sizes we want to use when modelling. In this case, we unselect the sizes we don't want and And we do the same choice also for elbows, butt-welded elbows. The suggested diameters are the same we've already chosen for the pipe. But we exclude smaller sizes because we will use socket weld elbows. We'll use socket weld elbows for diameters less than 3 inches. The same choice will be repeated for equal tees, so butt weld tees for 3 inches and more. Socket weld tees for diameters less than 3 inches. We also add half couplings. Socket welded half couplings for 2 inches and smaller. We load the flanges according to the standard, in this case ASME 150 LB RF WN flange, gaskets, and standard bolt sets. At this point, our piping class is complete and we can start modelling. Before proceeding, let's give a last check and then create an Excel sheet that shows us all the choices we've made in our specification. This is the list of components we added to the class. In the attachments area, we can go to choose a set of additional rules. For example, if we want to show the nominal diameters in millimeters or inches, or decide what type of automatic joint to apply in case of pipes longer than the commercial length. Here we have a maximum length of 12,000, so every 12 meters the pipe will be split. And we can decide how, with coupling or flanges. Here we give a minimum length to the pieces of pipe, because under a certain length the pipe cannot be welded or threaded. Here we define how many millimeters are required for butt weld connections. In the branch table, we have a table that shows all the intersections for the different diameters. Main size and branch size. Here we can also operate manually to add or remove components, according to our project choice. For example, we're going to add the B-codes that are the branch connection. Here we don't have any components, so we weld the pipe directly on the other pipe. We are ready, and we can proceed with the modelling. Let's now model in 3D the lines that we've previously drawn in P&ID. We draw a pipeline axis and choose the line number from the project database. In this case, we choose 9700 line. It's the same as that chosen in P&ID, so also the process data are the same. We provide a starting point, the nozzle, and through Connect option, we make ASA Pro seek for possible paths. The paths are shown with a yellow pipe to check for possible clashes. Now we dress the pipe axis. All the components, flanges, gaskets, etc., chosen in the class are automatically inserted. Now let's add a valve. We select the pipe on which we want to place it, and the contextual menu obviously shows us only compatible valves. Once generated, the valve can be freely moved or rotated. The valve is attracted by the pipe snap points, and we can change its alignment point. In this case, we're typing the distance between the valve center and our nozzle. Now, let's associate the inserted 3D valve with the corresponding P&ID object. Then in the Compare with P&ID palette, select the line just drawn, line 9700, which is not yet complete because it is wide, and link the valve. Since it was the only component over the line at this point becomes green, and we see the same information also in the diagram. To draw the next line, we will use the reference plane icons. These icons are special objects that we can place in the model to mark what are to be considered reference points. These are points that we can use as a starting point or as simple geometric references. In this case, it's an ending point, the nozzle, and another point is the axis of this pipe, because the line we want to draw must be exactly aligned with this existing one. Another reference point could be a point taken on this beam. Then click a normal AutoCAD point, type a distance from the point, 300 millimeters, and then we go up by 150 millimeters. Once inserted, the icons are scaled automatically so that they are visible regardless of the zoom factor. Launch the Follow Line command and click on Continue Line. With this option, we can continue to draw an existing line. Instead of typing the length, we select the Plane option and the software draws the line automatically so that it intersects the selected plane. In this case, we intersected the green plane. Now select the red plane, and then we go down until we reach the magenta plane. In this way, you can draw a 3D piping line without having to specify any length. To delete the reference planes, you can use the normal Erase command, or the Erase option of the same command used to place them. Here we can verify that a gasket with its bolts has been inserted. The crosses represent the gaskets that otherwise would not be visible. With the Flange command, we add a connection flange. Also in this case, we are not asked for the type of flange to be inserted because it's obviously been chosen previously in class. Now let's see how easy it is to create and modify pipelines with Azer Pro 3D Piping. Let's go draw a pipeline by typing some lengths. The line 9701 starts from an existing pipe and we type a distance, 500 millimeters, half a meter. And we go up to 1000 millimeters. The reduced T is automatically inserted because it was included in the branch table. And draw another horizontal pipe. So far we've drawn in orthogonal, and if we disable F8, AutoCAD's classic ortho function, we can draw a slope, so we can simply specify direction. We type the two components, and in this way we can go to size our slope. The 90-degree elbow is then sliced to fit the new angle. Insert a flange. And now let's go check what has been done. Here we have an elbow that initially was 90 degrees and now has been sliced at 33 degrees. As you can see, the objects are simple solids which can also be edited individually. Now let's make a change. We use the simple Move command. Delete this elbow and draw a horizontal section of pipe. In this case, we draw only the axis. We launch the automatic dressing command and the line is automatically completed by the software. With the Stretch Lines command, we're going to stretch my pipes. We select the pipes we want to move, and we can specify a value for the distance, or snap to an existing point with the Pipe Snap function, the yellow symbol. In this case, we've snapped the elbow endpoint, and then the new pipe is perfectly aligned with the existing one. Until now, we've modified the geometry, but let's see what happens when we change the technical characteristics of a pipeline. We draw a 2-inch line, which starts from an existing pipe, and then an equal T is inserted. To this line, we add a welding neck flange. And from the class, we pick a flange globe valve. The valve carries its own counterflanges, gaskets, and bolts. Also, these flanges are welding neck. Let's go to 2D wireframe and let's change the diameter. From 2 inches, change it to 1 inch, The components to be replaced will be highlighted in yellow, and Azer Pro 3D piping replaces the butt weld elbows with socket weld elbows, while the welding neck flanges are replaced with the corresponding slip-on flanges. The line geometry in this case has remained the same, but the technology with which it was made has been updated. Let's see how you can get the material lists. First, we launch the data extraction command, which allows to update the project database with the materials we have on our model. The database has been synchronized so the first lists can be extracted. We can get an Excel sheet with several lists: components, lines, beams, insulation, and welds. The components list is the piping materials. We select one or more drawings and launch the computation. A spreadsheet is generated with a set of columns that we can filter. In this case, we only want to see the materials that have the diameters of 4 and 3 inches. And beside the description of each component, we find the total quantity. The way the materials are grouped together depends on how you set up the list generation grids. The name is List Templates, and they are customizable grids where you can choose the fields you want to show. In this case, we have a list model that shows the fluid as first column, so if we use this model, the materials will be totalized not only for diameter but also for fluid. Let's now create a preview on screen. The fluids are AI, BB, CH, and for each fluid we find the materials divided by type and diameter. So according to how you customize the list model, you can get different outputs. We can also count the beams. In this case, we see the shapes that were used with their area and length in meters. With insulation list, we count the insulation that has been used in my plant. And the joints table, with this table it's possible to count the welds. Not only welds, but more in general, any kind of connection. BR are the branch welds, BW the butt welds, and SW the socket welds. Also in this case, they are grouped by diameter, thickness, material, and at the end we have the quantity. We are ready to get the 2D drawing from our 3D model. We are in the AutoCAD layout environment, and with the Create View command, we create a plan view. We choose the viewpoint and set the view scale, 1 to 50. Resize our window and place it within our page layout. With the same command, we can create an orthogonal view. An orthogonal view is a view with the same scale but tilted by 90 degrees. In this case, we get the front view. Let's stretch the borders of my viewport. OK. And the second view is ready. As a third view, we will create a section view. A section view is created by starting from an existing view and specifying one or more section planes. We added 2 section planes, so we get back a plan view, which is a stratigraphy, or the objects below the plane A and above the plane B are hidden. The fourth view is an isometric view, maybe a detailed view, so we set a scale factor to 1 to 25. We include the part we are interested in. OK. And let's arrange our drawing. These are still normal 3-dimensional views, not yet a 2D drawing. We hide the edges, and now we get the 2D drawings using the Draw Profiles command. Here we have the possibility to create a 2D drawing keeping the same colors of the original model, or just black and white. We can choose whether or not to project axes, gaskets, hidden lines, and many other settings. Let's now select the views to be projected. Right now, Azer Pro 3D Piping is calculating 2D profiles. This means that at the end of the process, a drawing made of 2D entities will be created, i.e. lines, arcs, and circles. which will be the exact image of our 3D model. Let's go to check the final result. This drawing can also be sent externally as a normal AutoCAD DWG. Now let's go add the dimensions. The ASA Pro dimensioning command is very similar to the AutoCAD linear dimension command. This dimension is not available in AutoCAD, it's the altimetrical dimension. With this command, it's possible to show the pipe axis elevation, center of pipe, or, according to the mode, the base elevation, bottom of pipe. For example, if we want to show the stand height of this pipe, we can use the base elevation. The settings are managed by AutoCAD, so dimensions respond to normal dimension styles. The annotation commands allow you to show labels with which the tags of the items are shown. This is the name of pump PMP 6700. And let's label a valve. In addition to the items, you can go to tag the pipelines. Through the Working Options window, we can then choose the annotation type. Annotations can contain free text or information fields. In this case, we will show the tag of line 6177. Let's go to tag another line. OK. The string composition that shows the line tag is an option that is common to ASA Pro P&ID. As a general rule, changing the line tag's composition has an effect on both products. Let's return to our 3D model for isometric sketch extraction. With the ISO Groups management, we can decide how to organize our sketches. The Automatic Groups function initializes a set of sheets, each one containing a set of objects. These sets of objects, sheets, will then become real drawings, isometric sketches. In the right column, we see the number of entities that ASA Pro is going to insert in that drawing. Here we are highlighting the sketch number 9700. And here we highlight another sketch. In this case, this pipeline would be on one sheet and this branch on another sheet. But we can also choose to merge the two sheets. So if we select the first sheet, we may then decide to add this line to it. In this way, we can rearrange the sheets as we find most useful. We spared a page so the empty sheet could be deleted. Once my sheets are organized, we're ready to extract a set of files with the ISO extension, which is the file format read by ASA Pro Isometrics, which we will see later. We extract 3 lines, 1, 2, and 3. For each sheet, an ISO file is generated and will be imported into the ASA Pro Isometrics module. The piping part is complete. We will now see the sketch part. In this part of the video, we will use the ASA Pro Isometrics module to automatically generate isometric sketches from the 3D model. We are in the ASA Pro Isometrics environment, and we are now going to process the ISO files generated by the ASA Pro 3D piping module. We select the 3 groups. Here we have a series of options that allow you to modify the sketch's direction. And here at the bottom we have the saving paths of the DWG files. There is an entire setup environment that can be customized by the user. Now let's run the Generate Sketch command and we'll see the isometric sketches production with a totally automatic process. A title block is inserted. A first sketch generation is attempted to calculate the graphic extension. Then a second adjustment is made to better optimize the space. Once the single line sketch is generated, it is automatically dimensioned. On the top right, we also see the 3D model as it appears in the piping, and on the right side we see the BOM tables as well as all the position balloons. The second sheet, the 6177 line, also in this case the sketch is resized. Automatic dimensioning. And finally, bill of materials and cutting list. Here we've generated all possible tables, so in addition to the bill of materials, we have the welds list and a cut table with all the lengths for each single pipe. Let's open a sketch that's already been generated to see the final result. On the upper side, we have the piping model as it actually is. Here below, we have the isometric representation with all the information, dimensions and material balloons. 5 equals valve and 4 valve 6 equals flange gasket bolts. This is the valve tag, and these are the welds W7 and W8. B is the piece of pipe. Each tube is marked with a letter. Here we have the bill of materials split into two sections. The materials for prefabrication and erection with their weights and quantities. Below we have a table with the welds. Each weld has a name and characteristics. BW equals butt weld with its materials and thicknesses. And this is the cut table, so beside each pipe we have a letter. Below we have the process data, then PED table with line pressures and temperatures. Here we have continuation references between sheets. The sketch is already very easy to read, but it can be further improved. With the Edit Dimension command, you can rotate the dimensions or stretch it. It's a very useful editing tool because it can help you solve critical situations when in a sketch we have overlapping objects. The same thing can be done with balloons. Let's now go to another sketch to see how ESA Pro Isometrics handles spools and adjustments. This is a sketch for the line number 9700. Here we have a welding W5 that we want to make on site. Let's go to insert the spool limit symbol. It adds an extra length to our pipe. And rename the weld from W5 to EW5, Erection Weld 5. The welded pipe is B, and clearly this weld will require adjustment. Currently the length 2645 millimeters. This is the length calculated by piping. We relaunch the calculation and see that the pipe B has become 2745 millimeters. ESA Pro adds 100 millimeters every adjustment. This is clearly seen also in the total materials. With the optional ESA Pro spool module, you can go one step further and make ESA Pro Isometrics to automatically identify the spools, assigning to each of them a label that can be a letter or a number. In this case, 3 spools were recognized. Spool 1, spool 2, etc. Once the spools have been detected, we can generate some labels that show them to me in the drawing. The spool 3 is from flange to flange. In the project options, we can also activate the subdivision of the bill of materials by spool. Show spool in prefabrication materials list. This is the text label that will divide the materials. Let's launch the Generate Tables command. And at this point, the prefabrication materials will be split into 3 subsections. For each subsection, we will have the materials needed to make that spool with their weights.